Dear friends, students and learners, welcome to the present session. I am Dr. Shashank Shrivastava from the School of Engineering and Technology, Indira Gandhi National Open University. We are discussing our material science course. So in the previous session, we discussed about the composites and its various properties, its elastic modulus and different types of fibers also. So further, we will discuss the composites also and adhesives as well in this section. So we start with the materials used for the composites. So composites actually they represent a very wide range, and from very common as discussed previously also reinforced concrete to metal fiber composites of high strength, all these things are in use. The strength of any material actually is governed by the defects, and these defects in solids may be dislocations or micro cracks or inclusions. So the lesser number of defects, the better is the material. Similar is the case for the composites. But the number of these defects actually tend to increase with size and surface area of the material. That is a very common thing, because a smaller size, lesser will be the number of defects, and larger size, obvious, it will have more defects. Such material fibers and viscose of a small size actually have been developed, and viscose are single crystals free of dislocations. So very small type of things that viscose, they are free of the dislocations. They are also coming under the category of composites. Glass fibers now, first of all we discuss this thing. So these fibers have certain properties. They have high strength to weight ratios, good dimensional stability also. They are very good in temperature resistance, and they have low water absorption property, and they have good electrical insulation also property. So accordingly they can be used in various places according to these properties. The glass fibers actually show good response to fabrication. They can be easily fabricated and also are cheap, and they are less costly. And there are two types of glass fibers. One is the E glass fiber and the other one is the S glass fiber, and both are commercially produced, and they are generally used for high electrical insulation and also where mechanical strength is required. Glass fibers actually are produced by drying them from glass melt drying process. You can learn from the manufacturing science. There's a drying process where they are produced in the form of fibers or wires, and in detail you can learn from manufacturing science. And they are available in the form of yarn, woven rovings and mats. Then from the glass fibers we move on to the carbon, aramid and boron fibers. These are certain other fibers used in composites. So carbon fibers are most commonly used reinforcement in plastic type of matrix. They have low density, high strength and high modulus of elasticity, but they are very costly at the same time. Then there are the aramid fibers. These are basically aromatic polyamide fibers, aromatic compounds, and these are also commercially available and mostly in two forms, that is the Kevlar 29 and the Kevlar 49. So this term is very common. Kevlar, this is very famous, and Kevlar 29 is known for high strength and low density, whereas Kevlar 49 has higher modulus of elasticity. Then there are the boron fibers also. They are known for superior stiffness, and their stiffness is actually next only to the graphite viscose we discussed earlier, graphite, and its density is comparable with E-glass. So what are the advantages and disadvantages of various types of fibers? Like carbon fibers, it is better over the E-glass in terms of strength, modulus of elasticity and density, but then these carbon fibers are brittle also. And the disadvantage, one more disadvantage, they are susceptible to oxidation as well. These carbon fibers, they can get damaged due to oxidation. Then they lose strength with temperature. So at high temperature they are not very useful. Then further, glass fibers, they have distinct advantage of low cost. They do not oxidize, but they also lose strength with temperature. Then the Kevlar 49, it is high strength, ductility as well. So ductility is coming in Kevlar, and it has lower density. Modulus of elasticity is actually lower than that of E-glass, Then the boron fibers, they are very costly, they are susceptible to oxidation, but one very positive thing is that they don't lose strength at high temperature. So whenever we require some high temperature application, we can go for boron fibers, because the carbon is also not good at high temperature and the glass fiber is also not good at high temperature. Then the mechanical properties of the fibers. The properties of the boron fibers, graphite fiber, Kevlar or S glass and E glass, whatever we discussed, actually is shown in this figure. You can see this is a figure where the tensile this strain is given, and this actually varies between 1700 and 3400, this tensile strength megapascal, while the fracture strain, which is on the x-axis, you can see the strain, it varies between 0.4 and 4% for different kinds of material. So like you see, there is the boron type 1, so it's that tensile strength is very good, but it shows, the x-axis shows that it is quite brittle also, because fracture will take place earlier, whereas the E glass has very good elasticity property. From this figure you can see for different materials it is given. Kevlar also is given, E glass is also given, S glass is given, boron is given. So best combination of strength, modulus of elasticity and density actually is available in carbon fibers. So the best combination of all these things, the properties which we need, comes out in the carbon fibers. That's why they are so much in use. So because they are so much in use, the carbon fibers, we need to know about the carbon fiber production also. So carbon fibers are made from polymer fibers, and the process is that they are a jet is thrown, a molten polymer jet is thrown in coagulating bath. Fibers so produced are then wound on frames and are heated to 250 degrees centigrade to oxidize these fibers, which will shrink and turn black. These fibers are further carbonized in a furnace at about 1000 degrees centigrade, and further they will be heat treated at 1500 degrees centigrade and 1800 degrees centigrade to get high strength and modulus of elasticity respectively. So for high strength heat treatment is done up to 1500 degrees centigrade. For modulus of elasticity increase, the heat treatment is done up to 1800 degrees centigrade. The polymer base of these fibers comprises of acrylic polymers, polyacrylonitrile, PAN or rayon. The PAN and rayon based fibers are costly. So rayon you must have heard, sometimes we are using in the class also. Then after discussing about the fibers, we move on to the next part of the composite, which is also important, that is the matrix, because we have two things, the matrix and the fiber, both in the composite. So what are the matrix metals? Matrix materials of varied nature can be used with the commonly used fibers like carbon, glass and Kevlar. And carbon fibers are used in the carbon plastics, metals, glass and ceramics. Glass and carbon, we know both are very brittle, and metals actually are very heavy as well, as they do not wet carbon fiber well. And then we come to the ceramics. Ceramics have very much different coefficient of thermal expansion, and their best quality of high temperature resistance actually cannot be used in association of carbon fibers. So if we see that we want to make a composite of carbon fibers and ceramic, then it is not possible, because then there will be no high temperature resistance in that case. And plastics actually only come out to be the best suited matrix material for carbon fibers. So from this discussion we have seen that ceramics cannot be used with carbon fibers, and other types of materials also cannot be used as the matrix for these carbon fibers. So best thing is the plastic. The plastics used as matrix materials are these polyesters, phenolics, polyamides, thermoplastics and epoxies. These plastics can be used as matrix materials. And these materials have one thing they have great restriction in respect of the temperature. So this is somewhat a negative aspect. Like polyesters and thermoplastics, they can be used only up to 100 degrees centigrade. Epoxies can be used only up to 150 degrees centigrade. Phenolics can be used only up to 250 degrees centigrade, and also they have the poor mechanical properties. And polyamides are the ones which have got good qualities at higher temperature also. They are better at 200 degrees centigrade above, but they are also not usable if we go up to 400 degrees centigrade. So we now talk about the epoxy matrix. Since we have seen the carbon fibers, can they club with the epoxy matrix to form the composite? So epoxies actually suit carbon fibers more than any other matrix material. Why? Because of the very good adhesion. These two materials, they form a good combination, bind with each other very easily and with great strength. So epoxy is a very good matrix material for carbon fiber. And these epoxy resins actually have better strength, higher cost, and used as matrix for not only for carbon but for aramid fibers also. As composites, their typical applications are in the aerospace, marine and automotive engineering. And in these areas, carbon fiber reinforced composites are replacing metallic materials for their high strength to weight ratio. Like I discussed earlier also, these carbon fibers reinforced composite, they are very good. They have very high strength, and at the same time they are lightweight. They have a strength as much as steel, and they have lightness as much as aluminum, or even better than that. So that's why they have been used even in aerospace applications. Along the length of the fibers, these composite can develop a tensile strength of about 1800 megapascal with a modulus of elasticity of around 150 gigapascal, and their percentage elongation but is limited to just 1.2%. Unidirectional composites have very low transverse strength and modulus of elasticity. Like earlier we discussed, this is a directional type of thing. So unidirectional composites, in the lateral direction, they will not have very good strength and modulus of elasticity. So for overall improvement in properties, how we can achieve that? By combining the unidirectional laminates at various angles. So this is a figure, this is a composite from multi-directional laminates. So we get good properties in all directions. So after the carbon fibers, we discuss the glass fibers. Glass fibers generally used with polyester as matrix, and they can develop unidirectional tensile strength between 200 to 350 megapascal, which is good enough, and the modulus of elasticity is also between 100 to 300 megapascal. So they are used with polyesters. The glasses are used with polyesters. In general, higher weight percent of glass fibers make the composite stronger, and as high as 80% fiberglass content is used in some cases. So in this case, we see that the matrix content has to be lesser, whereas the content of the glass fiber has to be in greater percentage for good strength. Equal strength in all directions is obtained if chopped rovings are used as reinforcing material, but the strength in this case is less than that with the directional strands. So we can use one thing is there is the chopped rovings type. So we can use this, we will get equal strength, but still the strength will be lesser than the one with directional strands. Glass woven cloth sheets are also used as reinforcer in plastic, but fibers lose strength at interlacing points due to interference. So glass woven cloth sheets act as a reinforcer in plastic. So it forms a combination to give a good composite. But the thing is that the points where there is a meeting point or interlacing point of two things, two fibers, then at that point there is interference. So the strength is lost at that point. And what are the applications of these glass fibers? They are used in boat hulls, the structures and building panels. All these things are the applications. They are used along with polyester. So this is fiber reinforced polyester, glass fiber reinforced polyester. Now we discuss the manufacturing process for the reinforced plastic parts. So these plastics actually are the reinforced because we are using the fibers, either carbon or glass fibers. Now we are learning about the manufacturing process. So there are two processes. One is the open mold and the other one is the closed mold. First process is the hand layup process. It consists of the following steps. We apply a thin coat of gel on the open surface of the mold. Then we lay fiberglass cloth or mat on the gel coated mold. Further, brushing the matrix resin on the fibers is done, and then the liquid resin is poured or sprayed. Then finally the accelerators and the catalysts are added to the resin before pouring. Further, the brush surface is rolled with rollers for removing entrapped air and spreading the resin evenly. So rollers are used for removing the entrapped air and for the spread of resin evenly, even distribution of the resin. The woven fiber or cloth are added as selective sites in the mold to increase thickness of the part as per design requirement. So the even fiber of cloth can be added at certain points wherever our requirement is as such. And again, the boat hulls, tanks and panels are made by this process, that is the hand layup process. So for these things we use the hand layup process. So you can see this figure is given here, and it is giving this process of hand layup. You can see how this resin is being poured, and there is the mold of a certain shape, and there is the laminate, meaning the layers are formed, and further roller is there which does the process of removing the entrapped air and spreads the resin evenly. Then we have another process, that is the spray process. It has slight variation in comparison to the first process, and it suits the requirement of larger size parts. So the earlier process can be for a smaller size, and this one for larger size parts. Here the fiber rovings and resins are used and fed simultaneously. You can see in the figure also, fiber rovings are fed through a chopper while a spray gun sprays the catalyzed resin. So both these things combine together. One is being supplied by the spray gun and the other is coming through the chopper. The rollers are used in the same way as in case of hand layups. Your function for the roller is same as in case of the hand layup, that is, removes the entrapped air and also spreads the resin evenly. So this is the process of spray. Further we discuss about the vacuum bag autoclave process. In the vacuum bag autoclave process, long carbon fibers are first impregnated in a resin and then they are laid out on a flat table. So it's a simple process. We can say that carbon fibers which are long, very long, length is more, they are mixed with a resin and then they are laid out on a flat table. After this epoxy gets partially cured, the pre-pregs are placed on shape tool in different directions and thickness. So according to our requirements, this thing, after this epoxy has been partially cured, this thing is placed on a shape tool according to our requirement to get different directional properties and thickness also. The tool covered with pre-pregs and desired shape and thickness is placed in vacuum bag, which is placed in an autoclave. So we get from the name vacuum bag autoclave process. So the process involves this vacuum bag and also the autoclave. And this process actually then causes the final curing of the epoxy. Then finally the part is stripped from the tool and finished to required dimensions. So we get the finished part and further finishing and processing is done to get the required dimension according to our need. Vacuum bag process results in parts of lightweight, high strength and stiffness. So this process gives us lightweight product and it has high strength and stiffness. Critical parts like the aeroplane wings, parts of rudder and cargo bay doors of space shuttle are made by this process. So you can see how important this process is. We are making certain things which have to endure very high temperature and stress. So, we see that this process, vacuum bag autoclave process, is used for aeroplane wings and all. So obviously it is quite costly and hence cannot be used widely. So next is the filament welding process, and from this what we get, we are seeing here hollow cylinders are made by filament winding process. How? We are using the fibers here, and they are made to pass through the resin bath, and then they are placed on a mandrel. So that way we can get the hollow thing. The wound resin fiber composite is then cured either at room temperature or elevated temperature on the mandrel itself. So while it is on a mandrel, it is being cured at a room temperature or at a different elevated temperature. After this curing process is done, the cylinder is removed from the mandrel, and this process results in high strength due to stretched fibers. Stretching is taking place and it gives us high strength, and is used for making pressure vessels, piping for chemicals and fuels, and also for casing of rocket motor. Here is the process in the figure. It will be more clear to you. See, this moving carriage is there, and the fiber is passing through the resin bath, and it is going on to the top of the mandrel and getting mounted there, and curing also takes place there, and after that it is removed. Then there is the closed mold process. So till now we had discussed the open mold process, now the closed mold process also. So glass fibers mixed with resin actually may be injected in a mold, and the chalk fibers actually are continuously fed on the top of polyethylene fill. This is another type of process, and on the top of the fibers the resin paste is laid, which is continuously covered with another polyethylene film, producing a sandwich sheet of composite. So suppose there is the fiber, this my hand is showing, the lower hand is showing the fiber, then on the top this polyethylene film is coming, then again I am placing another layer. So this thing will be a sandwich type of thing, and a composite sheet is being made. So this process is automated and continuous. These sheets are further stored in maturation rooms for 1 to 4 days. So this takes some time to be finally ready. So that is called the maturation time, and for that purpose they are placed in a special room for 1 to 4 days. And then they are cut to size, placed in a heated metal mold, and pressed under hydraulic pressure to acquire shape of the mold and uniform thickness. So according to our need, this process is done. They are heated and placed in a mold of a certain shape to produce that shape, and hydraulic pressure is also applied, and further we get uniform thickness. And this process is called the sheet molding compound process, and it is capable of producing high production volume of uniform products with good surface finish. And generally auto body parts are being produced by this process. So whatever in automobiles we are seeing, this process can be used there. So there is the process of pultrusion also. The structural sections of long length are produced by putting the fibers through resin bath, and then heated dyes are applied to get the specific shapes. So from this figure it is quite clear. There is a reinforcement roving. From there the fiber is coming on, like it is on a pulley type of thing rolling, and the fiber is coming out from there. And unidirectional fibers with high volume fraction and pre-tensioning process are capable of producing high strength. So you can see here unidirectional fibers are being used, and this process is known as the continuous pultrusion. So there is the resin dip tank also. There is the reinforcement roving. In the figure you can see it is much clear, and there is the orienter where it is moving the mixture of these two onto the heated die to get a certain shape. This is the process of pultrusion. So after discussing all these kinds of processes for making different kinds of composite, we move on to certain properties, that is the composite aspect ratio. Aspect ratio is equal to the length of a reinforcing fiber to the diameter. So this is the aspect ratio, when length of a reinforcing fiber is divided by the diameter. And In the so-called fiber reinforced plastics or composites, this aspect ratio is greater than 100. And if aspect ratio is less than 180 and more than 10, then the reinforcing phase is called the whisker. And if the length of the fiber is still smaller, that is the aspect ratio less than 10, then the reinforcing phase is termed the particulate. So there are two types we see, the whisker. Earlier also we have mentioned this thing in the session, and this new term is the particulate, where the size is very smaller, even smaller than the whisker. So now we will discuss about it. The particles, often called dispersoid in reference to their reinforcing action, are being used increasingly to produce particular reinforced composite, which we discussed just now, the particular type where the size was lesser than the 10. And these actually present several advantages over the fiber reinforcement. They are better even than the fiber reinforcement. But such reinforcement are better used in metal matrix than the plastic matrix. So such kind of particulate reinforced composite are much useful in the case of metal composite rather than plastic composite. And size of the particles vary from 0.1 to 1 micrometer, and when this is the case, then they are known as the dispersion reinforced composite. And when the reinforcing particle size is more than 1 micrometer, then it is known as the particle reinforced composite. So there are two things, the dispersion reinforced composite and the particle reinforced composite, depending upon the size of the particles. So further we discuss about this particular reinforced material. As regards to the mechanical behavior, the particulate reinforced material is closely an isotropic material, whereas a fiber reinforced composite is nowhere close to isotropicity. So it is quite obvious. You see fiber, it has got a certain length and it has got a property in a certain direction. In the other direction, the same property was not there. So it was not isotropic. But in case of very small type of particles, we don't get the question of this isotropy or isotropicity or anisotropicity, because they are so small, they have same type of properties in all directions. So it can be said that it is completely isotropic. Fiber reinforcement provides high directional strength in comparison to the matrix material, but it costs much more than the particulate reinforcement. So again, one more better property is coming for this particulate reinforcement, that its cost is much lower than the fiber reinforcement. If the requirement upon material is tribological in the sense of wear and seizure resistance, the costlier fiber reinforcement does not have as high resistance as the cheaper particulate reinforcement. So if we want to use it, suppose in bearings and all, tribological purpose, then particulate type reinforcement is much better than the fiber type. From particulate to whisker and to fibers present increasing cost. So as the size is increasing, as we are going from particulate to whisker to fiber, then the cost also increases. Besides cost, the particulate reinforced materials are less costly to synthesize and machine. So this is also a very good property, that to make them it's not very difficult, and machining is also not difficult in case of these particulate reinforced materials. They can be processed through casting or sintering with equal ease depending upon the application. And the secondary machining of particulate composites is also very convenient and cheaper. Other properties are also there which make particulate composite much better than the fibers and all, and these are like temperature and oxidation resistance. Then it has good damping capacity, so wherever vibration are more, we can use this thing. Then better electrical conductivity in case of the metal matrix, so they can be used as conductors also. And they have controlled thermal expansion coefficient, so its thermal expansion can be controlled. It's a very nice property because we can use accordingly wherever we need. The high temperature need is there, wherever else the thermal things are coming. So these are some good properties of the particulate type of reinforcement, and they can be used to reinforce plastic matrix, including chopped glass fibers, metal powder, sawdust, fly ash, and natural minerals. So they can be used for these things. And natural mineral particulates may also be used in the softer metallic matrix such as aluminum alloys, and natural minerals could be like granite, sillimanite and other similar materials. A very common example of large site composite is concrete. The cement is the matrix in case of concrete, while sand and gravel are the reinforcement. So our concrete itself is a particulate type of composite. But these particles have a variety of geometry. But if they are equiaxed or they have the same dimensions in all directions, and at the same time they are small in size, they provide very effective reinforcement. Even distribution of particles throughout the body of matrix is further helpful to obtain better composite. Modulus of elasticity of particular composite is function of the moduli of elasticity of materials of particle and matrix and their volume functions. It is quite obvious the things which are there, the constituents. So it depends on the elastic modulus of the particles which are there, small particles as well as the matrix, and in combination their volume function. So further we now move on to the adhesives. After discussing various kinds of composites, we discuss adhesives. So adhesive is a substance which is capable of holding materials together, and a joint is formed between two solids which are known as the adherents, with a thin layer of adhesive between them. So they are very much in use nowadays. We may have seen at various places, you also would have seen in experiments and all those things. And most adhesives are made by some kind of plastic only, either in the liquid or paste or solution type or emulsion, or even in powder form, which is this powder form is allowed to solidify and harden during the curing process. So it can be used in different phases also. Adhesives have distinction of making joints between similar and dissimilar materials. So this is a very good property, that even two dissimilar materials can be joined by the adhesives. Like for example, we may have seen plastic to glass adhesive is there, and glass to metal is also there, and metal to wood is also there. So all these things are there, but their strength is much less than like the welding joints and all. So what are the properties of adhesives? They are quite strong in shear and tension, but they are weak against cleavage or peeling. So peeling is also a process. I will show you with a figure also, like you are removing a certain layer from a substance. So that thing is not good for this adhesive. Otherwise in shear and tension they have reasonable strength. Then strength of the polymeric adhesive joint is significantly impaired. Why? Because of the presence of dust, rust, grease or oil. Hence the surfaces to be joined must be as smooth as possible, in which case only thin layer of adhesive will be required. So cleaning is very important in case of adhesives. Thinner the adhesive layer, stronger will be the joint, since the thin layers are void free and creepless. So defects are less in case of thin layers, the voids are less. And the adhesive film is generally only 0.1 millimeter thick. What are the constituents of these adhesives? They are made from thermoplastic, thermosetting and elastomeric polymers. So these are the constituents of the adhesives. Thermoplastic type of adhesives actually are prone to loss of strength as they become soft at high temperature. Yes, we have learned this in the earlier session also, that thermoplastic is not very good at high temperature. Temperature close to 100 degrees centigrade may not be permitted for this kind of thermoplastic adhesives. Thermosetting type of adhesives may be used at slightly higher temperatures, and these adhesives do not soften at high temperature, but still they also lose their strength. So thermosetting can go up to a certain higher temperature as compared to thermoplastic, but still it has also got limitations. Elastomeric adhesives are less sensitive to temperature, though they are similar to thermoplastic adhesives. So somewhat better is elastomeric type of adhesive because it is less sensitive to temperature, and better results have been obtained by blending the different resins in several proportions. So if we want to get even better results, we can blend these things, thermoplastic and elastomeric. Such adhesive blends are known as adhesive alloys. And what are the type of adhesives? The adhesives which have got very good bonding, and they are strong in bonding and have less creep, they are referred to as structural adhesive because they can be used in structures. so the name is given like that. An epoxy based adhesive available like in the form of liquid paste, which we discussed earlier, or even solid and epoxy blends with phenolics, nylon or polysulfide. These are all examples of structural type of adhesives. Phenolic adhesives between wood veneer, they are well known for their resistance to water and mold growth. So with wood we can use the phenolic type, so then we will not get the softening of the wood, or other type of creatures like termite or fungi may not come in. So phenolic can be added with this wood. For joining wood, melamine formaldehyde mixed with urea formaldehyde is preferably done. The above adhesive is normally available in powder form also. This melamine formaldehyde is available in powder form and is reconstituted by mixing with water before application. So we need to mix it with water. Then there are the non-structural adhesives also. They are based on the elastomers and the thermoplastics, but they are weaker than those based on the thermosetting ones. And many of these, particularly elastomeric adhesives, have good peel strength and impact strength. There is one polyurethane, polyester and silicone based one, and these are actually, this polyurethane, polyester and silicone are the basis for such adhesives. So after discussing the structural and non-structural type of adhesives, there are the natural adhesives also, and they comprise of starch, dextrin, soya, flour and animal products. Then there are the inorganic adhesives also, which are some of them are like sodium silicate and magnesium oxychloride. However, both these classes of adhesives, the natural and the inorganic, they are very much weak in strength as compared to the synthetic organic adhesives. So what are the characteristics of adhesives and the adhesive joints? I am throwing some light on this. This mechanical strength is good for these adhesives against shear and peel. And its toughness and resistance to impact is also good. Resistance to heat and moisture and other environmental degrading actions is also very good. Then it is also resistant to several fluids and chemicals, and it is the capacity or capability to spread evenly on surfaces to be jointed, thus having the wetting property. And what are the restrictions on these adhesives use? We need to be very careful while using these, because skill is needed for design of the joint and the bonding methods. And the service temperature, we know we cannot use it in very high temperature applications, it is restricted. Then curing time is also a very important factor, because it may range from a few seconds to higher temperature to many hours at room temperature also. So this is important factor. And a restricting factor, thermosetting adhesives require long curing time because they are of higher strength. And our designer or whoever is working on that must ensure that the joints are subjected to compression, tension or shear, but they should not be subjected to peeling type of force, meaning a force which tries to remove that layer should not be applied on it. So here are some types of joints in case of the adhesives, you can see in the figure, and from here you will get clarity about the peeling action also. This is the first one, is the single lap joint. You can see they are both coming together in an overlapping type of form, and then there is the double type of lap joint, meaning one layer in an overlapping form over the other, and the third layer is also coming in. So this is double lap joint. Then we have the tapered lap joint, the tapered line you can see in that. Then we have the butt joint, simply one over the other. Then the peeling action, finally in the figure you can see how one layer is being removed. So this kind of force, if it is there, then it is weak. The adhesive gets weak in the peeling type of force. Certain advantages and limitations of adhesive bonding. Advantages are like these: maintains the appearance of the surfaces. So in adhesives we don't need any kind of drilling and all. Riveted and bolted joints, we have the drilling and all. So in that way this won't weaken too much. And uniform distribution of load on interface will be there. because of this, and that will further lead to no stress concentration, and further the original strength will not be affected because we won't have any stress concentration. Structural adhesives are primarily meant for providing strength, while non-structural ones are meant for the purpose of sealing, insulating, preventing corrosion between dissimilar metals, also for dampening vibration and noise. Category is also according to the uses, applications. So structural are used for different purposes and non-structural for other purposes. Adhesives contribute little to weight when used to join thin parts, so it is very good. They will not affect the weight of the original material, and fragile components can be conveniently bonded as no machining is needed in this process. Materials to be jointed may be porous and may have very distinctly different properties. So for these purposes also they can be used. And heat sensitive materials can be bonded, since use of adhesives never requires temperature exceeding 200 degrees centigrade. What are the limitations for these? High temperature and strength actually is not good for these materials. High temperature application cannot withstand temperature above 120 degrees centigrade. Also the strength is limited, and most metals joined by adhesives cannot be stressed beyond certain limit. We cannot go to their highest capacity, ultimate tensile strength. Bonding time is also very long, and bonding requires elaborate tooling. It may require certain time, meaning it may require a day or two or even more. The surface preparation for making a smooth, dust and grease free is quite tedious and costly. So as we saw earlier also, that the dust and all affect a lot on these adhesives. So we need to prepare the surface, and it's a difficult process. And it is difficult to test a joint non-destructively. If you want to test an adhesive joint, then it cannot be done without destroying it or damaging it, especially in the case of large structure. And then the reliability of the joint is always low in service. So in this session we discussed about the different kinds of composites, how they are produced, what are the processes to produce the various kinds of composites, and finally we discussed about the adhesive material also and their various applications. This finishes our unit of plastics and adhesives. So we will now take up a new unit in the next session. Thank you very much.